Hello everyone and welcome back to the Func Prog podcast with me, Christopher. Today I'm talking with Fernando Borretti, who is the creator of the Austral programming language. Austral is a systems programming language, which means it kind of occupies the same space as, Rust, Sig, Odin, etc. But what makes Austral special is that it uses linear types for memory management and other resource management like TCP connections, file handles, etc. I won't dig too deep into it here. Instead, we'll leave that to Fernando. With that said, welcome to the podcast, Fernando.
Thank you. I'm delighted to be here.
Yes. And I think we should just jump right in. What is Austral? Is that how you say it, by the way? Or is it more like Austral? Austral?
That's a good question. In my head, I think I say Austral.
Austral.
Yeah, with the U as in the IPA. But I guess in English you could say Austral. That's more like an O sound.
Yeah, I'm thinking of Australia, which is not coincidental, I guess.
It's a Latin. Well, it's not quite. I mean, I moved here after I started developing the language. Actually, it's the Latin word. It's an adjective actually, rather than a noun. It's a Latin word that means southern. Like Australia comes from Terra Australis, and you have the boreal hemisphere and the austral hemisphere, and the boreal lights and the austral lights.
So how come you gave it the name Austral?
I don't know. I thought it's a nice sounding kind of like euphonious word, and there's no name collisions. There's so many. It also doesn't start with the letter B. B as in vector, not Bravo.
Yeah.
Because there's so many languages like Bal, Bale, Bala, B, Lang. There's so many languages that start with B. It's like actually a low density area of the programming language naming region. It's languages that start with A. It's just APL and ADA and not much else.
Okay, so it's like it makes sense from an alphabetical point of view as well.
I suppose, yeah. I just thought the word sounded nice, and it didn't have any existing collisions.
And then you actually moved to Australia as well.
Yes.
Is that what they call nominative determinism?
I think maybe it had been in my mind for some time.
So, yeah. But where did you live before you moved to Australia?
I'm from Uruguay. I was born in Uruguay and lived there basically my whole life until I was 24 years old in 2019, and then I moved to Australia.
Okay, but the work on Austral had started before.
Yeah, it's actually kind of embarrassing to talk about when the work on Austral started, because it's been going so long, kind of like on and off. I think that the idea of like building a programming language, like a low-level programming language with compile-time memory management in some way, I had that around like 2015, 2016. Okay. And then in 2018-ish, I built like a small language. Yeah, a couple of languages that were kind of like a tech demo language. It was like a little Lisp, a couple of Lisp languages with some compile-time memory management features. And then
so that was like a feature from the beginning.
Yeah. That was I think the first characteristic. It's actually what I started wanting to do was I started wanting to build. Because around like 2012, 2014, I was really into Common Lisp.
Okay.
And I was curious about building a statically typed, low-level dialect of Lisp. And I built a couple of those. Never really went anywhere. And then kind of the idea just very gradually drifted into a language with a lot less of a focus on the metaprogramming and the macros of Lisp and a more normal syntax, and it kind of gradually evolved into like the current version of Austral.
Okay. So how like in a nutshell, what is Austral?
It's a low-level language with linear types. Is the one sentence description, one liner.
And it has kind of like an ML flavor to it as well. It has some types, right?
Yep.
And so I guess listeners, I mean, from what I've seen, it kind of reminds me of the other ML, like maybe a bit more OCaml than Haskell, perhaps.
A little bit. So in terms of like types, it has records and it has some types, and that's kind of like all you need in terms of expressivity. So yeah, you have your sum types and your product types, and that you can build everything you want from that, other than runtime dispatching, like classes. And in terms of there's type classes, which are borrowed, they're essentially Haskell 98 type classes, and those are for doing ad hoc polymorphism in a tractable way. So basically, the generic print function is implemented through type classes. That's kind of the ML flavor. The thing where the similarities stop is that it doesn't have something like the ML module system, where you have signatures, structures, and functors.
So it departs from it in that way.
Yeah, it's a bit more imperative and procedural and low level than an ML family language, which is more meant to be functional.
Yeah, but something that I found interesting is that I guess what makes it stick out is the use of linear types for resource management. Can you tell us a bit more about, maybe first, what is linear types? We can start there.
Well, okay, let me think of an explanation. I think one way to think of it is that you have all these types which represent resources, and resources are things that have a particular life cycle, which is determined by side effects.
So it could be example, like an TCP connection or a piece of heap.
Like a trivial example. Yeah, like a trivial example would be a block of memory allocated from the heap via malloc. If you picture it like a graph, it begins when you call malloc, and then you can read and write to that memory in any order, in any number of times, and then this life cycle of that block ends when you call free. And this like, you can think of it as a graph where the nodes are operations and the arrows are like, an arrow from A to B means that you can perform A before performing B. So if you picture as a graph, you have a node for malloc, which flows into, and then you have nodes for read, write, and free. And there's an arrow from malloc to read, write, free, and an arrow, a circular arrow back and forth across read and write, and then an arrow from read and write to free. If you can draw that in your Visual Spatial Sketchpad. So that's like the life cycle. And the missing arrows are like the things you cannot do. You cannot go from free to write, for example. You can't read or write to a block of memory after it has been freed. Analogously with like TCP sockets, database handles, file pointers, all these like objects that represent some external resource. But programming languages don't really have any means to enforce this kind of protocol. Type systems, they're about shapes, more or less. They're about making sure that the square doesn't go into the circular hole. But you cannot enforce things that happen across time. You cannot enforce that. You can't try to write to a block of memory after it has been freed. You cannot prevent double free errors, and you cannot prevent protocol misuse errors. And there's a lot of like, you can try to do this with static analysis, right? But the problem with the static analysis is that it can show the presence of bugs but not the absence, right? It has false negatives.
Yeah, sort of like testing, I guess.
Exactly. It's it can show where there's a bug, but if a static analyzer doesn't find like a concurrency issue or whatever, you cannot be certain that they're absent, because I forget the term from logic. There's a corresponding concept in mathematical logic here. I think it's like completeness or something.
Oh yeah, the I guess it's like, you know, completeness and soundness.
Soundness, yeah.
Because like they're now I'm probably gonna mix this up, but so like soundness would mean that, like, you know, a given property always holds. I think, and the completeness is like, you know, you can express like
there's a proof.
Yeah, exactly, and like all have one has to do with like, okay, what can you express in the type system, and what other things like, you know, are not, or rather like soundness is that everything that type checks should work. But you also have the inverse, that like, you know, it's not, something might work but it might not type check. So
yeah, that's actually what completeness is. I'm missing my concept, but the point being that there's programs which are invalid but will type check, or like pass the static analyzer, which I suppose corresponds to unsoundness. So, you know, the good thing about type systems is that they're sound, unless you're using TypeScript. They're sound, and, you know, except for recursion and whatnot, and they're complete. You know, so like you can just sound means you cannot type check an invalid program, and complete means that every program can be type checked that is valid.
And I mean, usually there's some tension there as well. Like, you know, it's like it's hard to get both. As far as I understand.
Sorry, I feel I'm drifting, as I always do. I'm drifting back into like a bullshit mathematical logic topics. You ask me about linear types, and I'm already completely off the rails. No,
but it's I mean, this is a podcast about functional programming. So yes. I think the audience has more tolerance than usual for this kind of thing. I like it anyway.
There has to be one honorary appearance of Gödel and Erbrand. But anyways, the point is, like, static analysis is a complete bullshit waste of time, because doesn't give you any guarantees. You want to design a type system that is kind of like correct by construction. You know, unless you write a program where the rules for the type system just prevent you from writing incorrect programs by some metric of correctness. And with linear types basically, they allow you to write programs where high-level protocols about the life cycle of resources, or protocols in general, are enforced at the language level. So you can enforce, for example, that memory cannot be used after it has been deallocated. You can ensure, you know, that that the methods of the API are called in the right order to respect the protocol. You can enforce, at a higher level, you can enforce concurrency. You can prevent a bunch of concurrency errors, because you just have one mutator at all times for all values. This is kind of what Rust calls fearless concurrency. And at an even higher level, you get this cool feature called capability-based security.
Yeah, that's right.
Yeah. So linear types, it's kind of like an elegant solution that has a lot of like cascading positive consequences. Basically the goal is to be able to enforce protocols in software, and to enforce the lifecycle of resources, and to get like safe concurrency and capability security. And the means is linear types. And
if I remember correctly, like kind of the thing with linear types is that every value has to be used once and only once, right? Is that sort of the essence of the thing?
Yeah, I think in Rust calls their kind of take on this, the fundamental theorem of Rust, if you will. It's the mutable SOR alias, XOR. So a value either has exactly one mutator, or it has infinitely many read-only references. And that is a property that applies at every point in time. So a value is either owned by one thing or aliased by any number of readers. So with linear types, it's kind of like a simpler version of that. Every value must be used exactly once. Doesn't mean that every variable appears once in the source code, but rather that it has to be used once, and this is something that has to be demonstrable from the structure of the code. So, for example, if you declare a variable and you use it in like immediately after in a function call, you can't use it again. But then if you use it in like one branch of an if statement, you have to use it in the other branch, or not use it in any of the branches. And if you use it, in a loop, you either have to like assign to the variable before the loop ends, or you cannot do that because the loop may run n times. So you basically have all these like syntactic level rules that prevent you from constructing programs where the variable is used multiple times. And what this gives you is, well, if a variable can only be used once, it only has one mutator. So there's no concurrency bugs, and because it can only be used once, it's always consumed. So you cannot like have memory leaks, and you also cannot have, when you free some memory, you cannot use it afterwards because like the variable is like consumed. If you call free on a variable p, well, p is consumed, and you cannot read, write, or do whatever you want with that block after.
Because the free operation, one thing I really like about this is that, I think when you actually use it, when I've been looking at Austral, checking, trying to grasp how it works, and that thing I think actually feels quite intuitive because, the way it like sort of works in practice, from what I can tell, like when you actually use it, is like, like you said, every time you use a value, that value sort of gets used up, can't be used again. So in order to do something more with this resource, you have to return it back again. So it's like, sort of like you said in Rust, you give away a copy to make the borrow, or not a copy. I should be careful with my words here. You give away a mutable reference, for example, and then like Rust type, the borrow checker tracks that, like, oh, you can't give away more references to this thing. But with linear types, it's like, you give something and then you immediately get something else back, and then you do something with it, and like you said, if you, for example, I guess if you, for example, deallocate memory, that thing doesn't return. The deallocation doesn't return anything, I guess. So then like, okay, there's nothing more I can do with it. I don't know. It's very elegant, I think.
Yes, I think so as well. It's the type signature of the function determines kind of like its role in the life cycle. So like, for example, a function that takes some arguments and returns a value of type t, that's the constructor. And a function that takes a value of type t and returns nothing, that's a destructor. And that's not like a language level distinction. The language doesn't know what is a constructor, what is a destructor. That's just implicit in the structure of the function signature.
Yeah. So like, you get a bunch of nice properties for free, essentially.
Yeah.
So can you say something bad about linear types?
Yeah, well, the naive way of implementing this is like, I suppose the purely functional way is that wherever you have an operation that is meant to be non-destructive, it has to take a type and then return it. Again, return a copy. So for example, an operation that reads a block of memory will take the pointer and it will return both like the value at that pointer and also the pointer itself. And internally this will be implemented in some unsafe way where the pointer is that like delinearized and then like copied or something. but the API has to remain linear. And the problem with that is it's just horrendously, it's very functional, but it's just horrendously inconvenient to be just copying everything all the time. It'll be like returning every function call takes a linear argument. You have to destructure the tuple that comes back. It would just be annoying. So there has to be a compromise kind of on ergonomics. And borrowing, as in Rust, exists as kind of that compromise. It allows you to locally relax the linearity rules in like a contained way, so that you can write code a bit more pleasantly. So code that only needs to read some linear value can just take a read-only reference to that value, and then you can borrow that value instead of having to pass everything around. It's also safer because a function that takes the linear copy and returns it, there's no guarantee that it's actually returning the same thing. It could be deallocating and allocating, for example.
Yeah, that's true. Like as long as it's the same type, I guess. That's the only requirement.
So it's actually borrowing. It's kind of like fine-grained kind of permissioning in a way. You can the linear type itself is the permission to do everything, and the read only and the read write references are kind of like sub capabilities that give you limited rights.
Yeah, so so if I get this straight, Rust is a bit more like the type system needs to be a little bit more sophisticated, but as long as you have like a mutable pointer, for example, to something, you can just you're free to do whatever with it. Don't have to think about it much. But in linear types, you sort of have to keep doing this thing where you continuously return like new references. Because I guess this is also, like you said something that I thought was interesting, like, it makes it more functional. I guess this sort of lets you, treat code as if it was referentially transparent as well.
Yes.
Like, at least if you, morally, from a moral point of view.
Yeah, I think linear code, I'm not sure if I'm misusing the terminology, like formally, but I find that in a linear programming language, you can write code as if it's referentially transparent, as if it has equational reasoning, but you can have efficient in-place mutation. So, for example, a function which takes an array and an index and a value and returns, the new array with that value at the index. In a functional programming language, it is conceptually returning a new value. And if it's doing in-place mutation, that's a compiler optimization. Whereas in a linear programming language, that function is it's like morally returning a new value. But because all the values are consumed linearly, you can do in-place optimization. But the function is the function has like the kind of properties you would expect from a functional programming language. It's not quite equational reasoning because you cannot treat it like a rewrite system where you expand the definitions in line. I don't think, but it's like morally referentially transparent. I find that it's kind of like you can write these APIs that are like very functional looking, but also very efficient.
Yeah, you don't have to make those how can I say, otherwise you sort of have to or we can back up one step and just explain if with referential transparency we mean the property that a function given the same inputs should always return the same outputs, and usually the way you accomplish this in most functional programming languages is that you sort of keep making copies of stuff, right?
Yeah.
Under the hood, that sort of means that you usually have to do a bit of clever optimizations to make this efficient enough to be used in the real world. I mean, for example, the canonical FP data structure is a linked list, right? Because it's very easy to make copies of a linked list. You just if you attach like a new value at the front of the list, I mean, that's essentially a new list. So that thing is easy. And then you have like stuff like caches, etc. It's a bit more difficult, but you end up working a lot with trees, etc. But like you said, in this case, it's sort of when you have this linear. Is it called like a linear argument? The extra return value, or or sorry, if you have linear types, anyhow, it's like you always return something, and I guess you can sort of in your head you can sort of think of that as like a copy of the state of the world at a given time. So you still get that property, and like you said, you can make it very very efficient.
You get the benefits of it's tractable and it's high performance.
And so when you like, if we look back a bit, like when you started designing Austral, like what was the intended use case? Like you mentioned low level programming, but was it like let's see, was Rust, when did Rust come out? Wasn't that around this time as well?
I think Rust came out in 2008. Or
that early? I thought it was much later.
Well,
but okay.
There's versions. I mean, I think the work started in 2006, and there was a first version in 2008. Because I remember doing a talk about this at work in 2013. And I think the 1.0 version came out in 2015 or thereabouts. Or if not 1.0, some kind of like major version came out then. I mean, not December major, but like an important milestone. And then I think in the late 2010s, it was just like concretized a bit more. And now we have the Rust editions, and now it's a pretty established, mature language.
Yeah, I mean, it's a lot of it feels like, I don't know, it feels like like systems programming space is like, I don't know, it feels really hot right now. Very.
Yeah, well, I wanted something that was like low level, but also a bit simpler. I wanted something that was a bit, because the approach that Rust takes, it's a bit closer. I think the idea is that you should have the developer experience of kind of like C++, but the security kind of like just happens. So you're not really encouraged to think in terms of like, here's how the borrow checker works. You're encouraged to just kind of like write code, and if it's reasonable, it will pass, and if it's not, it won't pass. Like you can think of the fundamental rule, which is a value is at all times either mutable, exclusive, or aliasable. But you're not really meant to be thinking about what are the minutiae of the borrow checker. And the borrow checker evolves over time, mostly in the direction of accepting more programs. I think it was like there's been a bunch of innovations. I forget the name of this one feature they added. It was something called like non-lexical lifetimes. They basically just add more rules to the borrow checker to like get it to accept more programs. And that's a valid approach. I mean, my experience of writing Rust is that it mostly just works.
So you're not one of those people who are like like clench their fists and curse the borrow checker.
No, I feel like that's honestly, a skill issue. To be honest, it's a skill issue. You just kind of like you can figure it out if you learn the language. You eventually figure it out. But what it does get more complicated is where features kind of start interacting. Like when you have either async or closures, or God help you, async closures. That's what it's like. Okay, what's a borrow checker going to do? It becomes empiricism, right? You have to write the code and kind of like figure it out. I wanted something that was a bit more on the ML side of things, whereas I wanted to distill this to like, okay, what's like a really simple kind of like kernel where we have a small system of basic rules that don't change very much, and we have this fixed system, and then you kind of just roll with that. And it may be a bit unergonomic in places, but it is simpler. The idea being like, when you look at some code in a programming language, you're mentally kind of running the type checker in your head. Maybe not all parts of it. You're not running the type inference. I mean, you're not running the type class resolution algorithm for Haskell 2010, which is probably very complicated. But you're mentally evaluating what is the type of this thing going to be, given what I know about the type of these functions. That's like an implicit process. You do it automatically because type checker rules they're mostly intuitive. I wanted something a bit like that, where it's like you can read the code and mentally run the borrow checker or the linearity checker and decide, this is not going to work because of this thing. This variable appears here, and so when the borrow checker errors happen, it's very clear why something happens.
Yeah, because like I guess in like you said in Rust, it's I don't know. The feeling is a lot more similar to C++. Like it feels kind of hard to intuitively reason about like why can or can I not do this, for example. But you wanted something that was a bit more intuitive.
I wanted something that was a bit more pared down. The thing with pragmatism is that there isn't really a limiting point to pragmatism, right? You can always make the language like more pragmatic, and just it grows and grows in complexity. I think one time I went into the Rust compiler to see how big the borrow checker is, and I think it's something like 28,000 lines of code, which is not I guess for a production quality compiler, that kind of volume of code is not surprising, but it's a lot of code. Compilers are surprisingly big, but I think one thing I was proud of with Austral is that the compiler is like a few thousand lines of code. It's a bit bigger than I'm comfortable with. And the type checker is pretty big, but the linear type checker, which happens after type checking, is pretty small. I could probably be made smaller because the way I built it, it's kind of very, very grog-brained. It's very simple.
Like explicit each step.
Yeah, it's like a very top-down, very clerical kind of algorithm. You could do it. I built it basically by doing the type checking by hand and then just like formalizing the decision process that I was doing in my head. Not the type checking, but by doing the linearity checking by hand and formalizing it. Whereas afterwards I realized, this is a bit too involved. There's probably some symmetries here that I'm just not seeing. And I had a vague idea for a better linearity checker that I haven't had time to implement. I might just write it as a standalone blog post first. You can probably do a graph-based version, which is much simpler than what I have right now. So you can simplify it even further. But
I was going to ask, like, did you, when you came up with the idea of using linear types, how did you come up with that? Like, what made you pick? Or like, I guess this is like two questions really. Like, okay, so one is, where did you get the idea to use linear types? And two, did you start from like an existing literature on the subject, like a paper or something like that?
Yeah. So this is what I wish I had been a bit more rigorous with, keeping like a lab notebook or like references on or notes on papers or whatever, I can be, and also particularly because this was years ago, this was a lot of like, staying up till 5 a.m. reading a bunch of like papers that are like way beyond my league. I don't have like formal theoretical computer science training. Like now I can kind of read those papers that have the Gentzen notation and all that stuff, because I have more knowledge of like logic and proof theory. But before that, I could read like the prose and I could read the examples. But when you go to the part where you have the inference rules for the type system in those PLT papers, it's like, oh my god,
like
what's going on?
The turnstiles and like
the turnstiles and the natural deduction inference rules. It was just completely incomprehensible. So it was. I remember being aware of region-based memory management. I remember being aware of the Cyclone programming language. I remember being aware of the early versions of Rust and linear types and Henry Baker's papers, and there's a whole bunch of PDFs that I had access to at the time, which describe in various terms, some more prosaic, some more theoretical, the various approaches, like linear types and region-based memory management. I can't quite say how much is my own kind of invention, how much is just like borrowed from the existing literature. I think one idea that I had, that it may be my own, but I don't want to like say this 100% sure, was the idea of having the different type universes, where this is kind of like kinds in Haskell, the types of types, where you have like the free universe, which is like the types that can be copied freely, unrestricted, like integers and booleans, and you have the linear universe, which is the types that are linear. And when you define a new type, there's a bunch of rules, if you're defining a record that only has free types, you can make that type free, or you can make it linear. So like you can kind of like you can just declare that a type made of free types is linear. That's how you bring new types into the linear universe. But if when you're defining a type, if it has linear components, like if you're defining a structure where one of the elements has a linear type, you cannot make that free. That has to be linear. So it's like just containment rules that like linearity is vital. So like a type that contains a linear type is linear. And these rules extend to like the type parameters. So for example, if you're defining a generic type that has a type parameter that belongs to the free universe, that type can be free. But if it's linear, it has to be linear. And you also have a version of like there's a type universe called type, which corresponds to star in Haskell, which just it accepts any type from any universe, but it behaves as if it is linear because there is a minimum common denominator. I'm having second thoughts about that. I think it's kind of cute. It's like nice. It kind of works, but it might be unnecessary. I think the way Rust does it is probably more elegant, where in Rust every type is linear, and some types implement the copy type class, which in Rust is called a trait, and copy the signature of copy is like, I think it takes a read reference to a type and returns an instance of that type, like a linear instance. So for example, the Boolean type is quote unquote linear, but it implements copy, so you can copy it, and the compiler can like insert the quote unquote call to the quote unquote copy method whenever you use a value of a Boolean type. Conceptually, you're calling copy. And similarly, when you try to like copy a value that doesn't implement that trait, when you use a a variable or a value that doesn't implement a trait, the compiler is like, well, there's no copy implementation. You're using this variable twice. That's an error. Yeah, I think that's possibly more elegant because first of all, there's only one type universe. There's no complex rules about anything else. And then like, if you want a type to be copyable, you just implement a trait, which is, traits are like the Rust version of type classes. That's an already existing language feature.
So they can sort of reuse that same mechanism.
You're using the same conceptual machinery, and you don't have to introduce this like whole new terminology. I like the idea of the type universes because it feels a bit like I don't know. To me, it's cute. I like it, but it probably has to go. It has to go. I think the Rust version is more elegant. You just reuse traits, and everything's like linear by default. Like in Rust, that's actually a surprising thing. It's like every type is actually, even if you don't mean it, every type that you define is linear, quote unquote linear. It doesn't quite work that way, but you have to like derive the clone or copy traits to make something unrestricted.
I have to say, like, I like, this is how you copy the thing. This is how you like work with the thing. Yeah, I'm not a big Rust programmer, so I'm not sure exactly how that works. But I see the point. But speaking of which, like, what state would you say that Austral is in? Like, is it closer to like 1.0, or are there things you still need to like iterate a bit more on before you can sort of say like, oh, this is the language?
In late 2022, I worked really hard on it, and I got to the point where it was like, it was usable. I would not call it like 1.0, but it was like the language, everything's implemented, like type classes work, generic, everything works. There's no like holes. The kind of kernel modules are implemented. The foreign function interface works. The tests were passing, and I was at the point where like I could build like basic data structure libraries for like the standard library, and that would work. And the compiler gave like decent errors. So I was like, breathed a sigh of relief, and I was like, okay, it's minimally done. And like I can write to the introductory blog post, and the website has like a tutorial that's like, minimally complete. This is kind of like the MVP. And I released it, and it got some attention. And I think by then I had kind of run out of steam because it was, part of it was because I had been working on this on and off for like so many years. And I would just kind of like try to build it and then run out of steam. Because compilers are surprisingly heavy and long to write, and I would just try again and so on. And this was during the period where I was like completely undiagnosed, untreated ADHD, so that's not super surprising. So when I got to the point where it was kind of the language was kind of usable, I was like, okay, well, I'm willing to take a bit of a break here and work on other things. And the 2023, 2024 was very much kind of like head down with work. And I was using Rust professionally, which was interesting. So I was not working very much on open source projects. And since 2 months ago, I've been like fun employed and just working on various little things. I mean, writing blog posts, reading books, working little software projects and experiments. And I think I might go back into it.
Okay. Yeah.
The things like, there's a number of things I will probably change because partly because my experiences with Rust have changed, and partly because like I have changed. So like, the language might have to change. Probably some of the weirdnesses, I'm a bit more willing now to get rid of some of those. And also I would like to if I resume work on it, I'll probably end up porting the bootstrapping compiler from OCaml to Rust.
Okay. Yeah, it would be interesting to get back to that as well. But before we do that, like you mentioned a bunch of things already, like the that you were thinking of changing in Austral, like the way the linearity checker works, and like using some kind of like type classes instead of type universes. But I wanted to ask, like in hindsight, was there anything you wished you had done different, like either in your process or the language itself? Like aside from also like what you said, like keeping lab notes. I guess that's a good. Like I think, have you seen Simon Willison's blog?
Yes, I think I have.
He's really good at like he has these little week notes, where he sort of like writes like a mini blog post about what he did that week. And I was like, yeah, that's a good idea. Like I should do that, and then I don't do it.
Yeah, I tried to, like, over the years, I've just developed this attitude of like, if you do something and you don't write about it, it just didn't happen. So I try to be a bit more open with like writing blog posts about little experiments that I do. If it could be like a tiny little experiment, I might still write a blog post about it. I think I might have been working on it in public a little bit more instead of just doing the thing I used to do, which was, just work on this obsessively in my little gargoyle cave and then put it out there on the internet and then tell nobody about it.
Done.
Yeah, it's done. Nobody will ever see it because I will never tell anyone about it. But yeah, I think yes, keeping a lab notebook, that would be good, because it would help me to first give credit to the ideas, like where do they come from, also to establish like a stricter genealogy of like where did these different ideas come from. It would also be good for myself to like trace like the evolution of the language, like on Tuesday 2018, 18 July, whatever the fuck, I had this like idea, I had this like breakthrough, and it's like, oh my god, this is so much simpler. Just kind of like a journal, a project journal, that would be good to have with references. Other things that I would do, process-wise, like building in public, keeping up a project lab notebook. Another thing is that I kind of wish I got into Rust a bit earlier, because I built the compiler. I started building it in standard ML and then in OCaml, and I was kind of still in that mindset of like, oh, let's use like these cool obscure languages. And see, the thing I discovered when I started using Rust professionally is that the tooling is so good. Like Cargo is such a pleasure to use. If the language was terrible, it might still be worth using because Cargo is just so good.
Okay.
And
what makes Cargo so like? Bear in mind, I think I've written maybe like 2 hours of Rust total.
Yeah.
So, but if you give me what's the elevator pitch for Cargo? What makes it so good? Because a lot of people are saying this.
Well, it's not quite the way I usually explain it is that it's not quite like a positive aspect. It's not like something that Cargo has. It's just the negative aspects. It's the thing that Cargo doesn't have.
Okay.
Most package manager / build systems, they just you follow the instructions exactly on the website, and everything breaks. Or you just have all these like little foot guns, like. You do something and it doesn't work, and then you learn like, oh, I forgot that, when I update the package.json, I have to run npm install first, or it doesn't pick up the changes. There's all these like minute little things, and like just constant errors, and just beating your head against the wall with these like inscrutable errors that happen. I mean, with OCaml, I had constant problems with the build system Dune, but it was like, just to create a new project, I would just follow the the instructions on the website, like run this command and this command and this command, and I would run the first command and it would break. And I'm like, okay, well, we're already off the rails at the first command. And then really simple things like, okay, how can I run a unit test? How can I profile my code? It's like, what are you talking about? We don't do that here. Like, just figure it out from first principles. The tooling was just, the default experience for tooling is just so frustrating. And it's the same with, for some reason, it's kind of the same in every language. It's kind of like Anna Karenina. It's every language has a package manager that is fucked in its own way. In Python, this is my favorite Python fact. Pip, the package manager, the way it does dependency resolution is it, instead of just like downloading an index, just the graph of package dependencies, and doing dependency resolution on the graph, and then downloading the packages that it has to download, it's kind of like this depth-first algorithm that just downloads every package and every version. And if a version doesn't fit, well, it just downloads another package. So the backtracking involves downloading packages, right? There isn't a separate dependency resolution step. The dependency resolution is mixed in with the process of like downloading packages. So you could download like a gigabyte of zip files to end up using 30 megabytes of dependencies. It's just absurd. And it's like, it's all like this, Maven, and then you just use cargo, and everything just works as designed. There's none of these weird foot guns. Everything's like decently documented. All the commands are named what you expect. So you just kind of like, you don't even have to read the documentation. You just kind of like type the commands that your brain says to type. And it's like, oh, that is the command. How do I type check a project? Well, it's probably like cargo check. Oh my God, yes, it is. And
that's really good design. Like, when you can sort of like just guess. Like,
so everything just works as intended.
Yeah.
And like normal things like testing, profiling, code coverage, you can just do those things. Formatting the code, linting, it just works. And it's such a huge boost to quality of life. And when I was using OCaml, I was like, well, the language itself is fine. I like modules. I like, the ML syntax and the algebraic data types and all that stuff. But that's all kind of like par for the course nowadays, right? Like every language has, a type system and some types that's worth using. And then just the tooling is horrible. And, OCaml has this parser generator called Menhir. I refuse to write parsers by hand. I need a parser generator, and it's really good. It has a lot of like really advanced features, especially for like error reporting.
Okay. But because people usually say like that's the downside of parser generators. Yeah.
The downside of parser generators is the error reporting. Menhir has this. It has this really clever feature for doing error reporting. It can. It's interesting the way they do it. But the point is, you have all these advanced features, right? And like, but can you use them? Probably not. Like, you're gonna find, because just getting anything set up is such a pain in the ass that you probably will just not change your configuration out of fear that you're just gonna break the thing. So you're just gonna settle on like the first thing that works. And yeah, that's kind of like the experience with OCaml. It's like, it kind of works, I guess. The language is good, but getting to the language, it's like a moat. Like Dune and OPAMs is like a moat. And admittedly, this is as of 2022. I haven't used it much since. I know that some people have been working a lot on like improving the Dune OPAM experience, and maybe that's improved since. But it was just such a living nightmare then. That yeah, just the idea of working on Austral again is like, it's cool, but like I would have to like install Dune and Dune again. Oh my god, no, thank you. It's just
you're getting like PTSD from last time.
Yeah, you get PTSD flashbacks from this. It's just emotionally easier to port the compiler to Rust, because Rust is like, it's like a decent language. It's like a good language, a well-designed language, and the tooling works. You know, that's one thing I would do. Just like lab notebook, work in public, port it to Rust.
What do else? It in Rust.
Yeah, rewrite it in Rust. By the way, what else would I do differently?
Yeah, but I think we can sort of pin that a bit, because I think there's something really interesting to unpack here, and I agree. Like, I haven't used OCaml that much. I actually started playing around with it a bit a few weeks ago, and so I'm coming into this with fresh eyes, and I think they have done a lot of work to sort of make this thing approachable. And I mean, I wouldn't say it's perfect. I did find like a small bug that I reported, but at least, like, you know, it's acknowledged that it is a problem, which I think is a huge step forward. And I've kind of had the same thing with, like, you know, with Haskell and Cabal. Like, I have this old Haskell project, and it doesn't build anymore, and it's like, you know, I don't know, it feels like, okay, I'm gonna go in there, and it feels like kind of, I'm gonna have to mud wrestle with an anaconda to get this working again. I even tried to get like ChatGPT to write like a Cabal file for me, and it failed miserably. But yet again, like, nowadays we have, you know, GHC up, for example, to like, you know, smoothen the Haskell installation thing a bit. But I think it is traditionally something that the functional programming community maybe has undervalued a little bit, like tool support.
Yeah, well, I think there's an argument that, and I often think this, that the core language is what matters, because that's immutable, and the tooling, like, that can evolve in the future. I mean, in a sense, that's right. You know, like, if you're working, you know, the tooling can be nice, but if the language has this core flaw, that's just not going to be fixed by like scaffolding around it, right? And yet, in practice, what tends to happen from that attitude is that the language remains good, but the tooling remains shit, and nobody, you know, the improvements, they're always in the future, because it's okay, well, we can in principle just do it in the future. And I think what you get there's a kind of feedback loop where the language has like bad tooling, no documentation, and a small ecosystem. You're selecting for people who don't read the docs because they can read the source code, don't need tooling because they build their own tools, and don't need an ecosystem because they write their own libraries. And, you know, people who are kind of like very, very self-reliant in the programming sense. And that's great, but those people don't need those things, and they also don't feel the need to contribute to those things, right? If you don't need documentation, you don't contribute to it. If you don't need tooling, you don't contribute to it. If you don't need an ecosystem, you usually don't contribute to it. So you just have this kind of like feedback loop where at every stage you're selecting for, in a Darwinian sense, you're selecting for people who don't care about those things, right? So and it kind of, I think I observed this with the Common Lisp.
Oh yeah, I was just gonna say.
Yes.
It feels like the Common Lisp is sort of like the OG. I mean, don't even call this phenomenon like the Lisp curse. At least I guess this is part of the what.
Well, there's the Lisp curse, and there's the bipolar Lisp programmer. There's a lot of curses around Lisp. But I think with Lisp, it's like the language has some interesting features, but the tooling is stagnated for so long that it's just kind of impossible to do anything practical with it. So at every point, you're just shedding shedding anyone who's not an absolute true believer. Yeah, it's kind of like in a cult when, you know, they predict the end times is going to be like 1977, and then that year rolls around and nothing happens, and like, but the cult gets like, you know, the belief gets strengthened, right? And what's happened there is like the people who are on the fence, they just leave the cult because they go, well, the end times didn't happen. But the people who stay, you know, they're the true believers. So at every point, you just get like evaporative cooling of everyone who wants to get something done. And you just get the people who are left who are really just obsessed with the purity of the language and don't care about the tooling.
Yeah, they don't care about like menial things like delivering software.
Yes, I mean, frankly, shipping software is vulgar and populist. The best code has never been written.
Yeah, but I think, I mean, there is something to that. Like I mentioned this book a bunch of times on the podcast, but that this book, Crossing the Chasm. Have you read that?
It sounds vaguely familiar. What is it about?
It's basically like, you know, the idea that, or it's sort of. It sort of disproves or debunks the falsehood that you know, early adopters of a technology will automatically sort of bring on late adopters and like the rest. It's sort of like a bell curve, like, you know, where you can sort of put like every user of a technology into one of these 4 buckets. The problem is that like the early adopters, just like you said, they usually don't care about the same thing as the late adopters do, and a lot of the times they have completely opposite interests. So, for example, like you said, early adopters, they're usually very self-reliant. They don't care about documentation. They might even relish the challenge to try to learn something without, like, you know, too much hand-holding, for example. And they sort of like being on the cutting edge, you know, because in their mind it's like, you know, I want to find the best tool for the job. But the late adopters, they sort of think the other way around, like, you know, they really want a lot of hand holding, and they don't really think in terms of like, okay, what is the best tool for this particular problem? It's like, what tool is everyone else using to solve this problem? Gabriela Gonzalez has a great YouTube video, or there's a presentation on YouTube on like selling Haskell to a mainstream programmer, where, you know, she shows how this applies to programming languages, and tooling in particular is one of those things. Like, you know, if I follow the directions exactly like you said, and it still doesn't work, like, you know, you're gonna lose a lot of like those late adopters.
I think at some point, I mean, I used to be very much the kind of like early adopter, you know, psychotic schizoid gargoyle who was like, I don't need documentation, I don't need tooling, I don't need whatever. I'm just like in my I'm just perched on a church steeple, waving my Lisp magic wand and making marvelous things happen. It's great.
Adding things to your Emacs config.
Yeah, exactly. And it's just like rising my desktop, and it feels empowering for a while, but eventually it feels very lonely, because there's just you cannot really build anything lasting without involving other people, and you cannot involve other people when like everyone else is kind of like on that same mindset of like, well, I'm just like a wizard in my wizard tower, and I'm just like all alone building these things. It's a hard problem to, I guess it's easier at the start because you can kind of like invest into tooling, and also it's easier to curate the vibes, so to speak, on an early stage. But it's towards like in an already established language, it's just kind of like it's just so much harder to like steer like the vibes, mostly because like nobody in the existing community or not many people will kind of appreciate work towards that. Like I think how I burned out OCaml Lisp was in 2016-ish. I made a website for OCaml Lisp that was meant to be this like modern, good-looking kind of like centralized information domain for Lisp. It was like, here's the tutorial, here's how to get started, here's a new, better-looking wiki.
You can sort of sell people on Common Lisp.
Yeah. Partly it's a bit a marketing thing, like a signaling thing. So the website was like good-looking and modern, but partly it was like it was meant to be like a centralized place for up-to-date information for beginners, which Common Lisp at the time didn't have. It was like there wasn't like a central shelling point for like, this is the tutorial, this is the wiki, and like I built it, I put it together, I got it out there, and I was still running on this mindset of like, if you build it, they will come. If you plant the flag, if you plant a flag, collaborators will come and they will help you like, fill out the wiki and fill out the tutorial and make it good. And like that didn't happen. And that was partly my failure of like failing to, actually ask for help and like promote it and get it out there and, like recruit lieutenants and assign work to them. But partly I think it was the community, kind of didn't really care. But yeah, this is the whole topic of like, obscure languages. They're obscure because it's the people kind of want them to be, in a sense, in an abstract kind of sense. They just they like being the wizard, and they don't like working on linters and stuff. So yeah, if I'm building like a I think I've lost the patience to be the Uber hacker. Nowadays, if the tooling doesn't work, I'm probably not picking it up. So if I'm working on like a little side project, I'm usually using something like Rust, because with Rust I can get started really quickly and have like tests and a CI setup that works. And yeah, Rust is a really tractable language for like prototyping actually.
Okay. It's interesting, and I guess like you always, the chance of having what you need available as a library is much higher in Rust.
Yeah, the ecosystem. There's a lot of people who still kind of think that Rust is kind of like this obscure, weird language and like an impractical choice. And it's like, no, the ecosystem is huge. At work, I never really had an instance where I needed some fundamental building block and I was like, oh, it doesn't exist, I have to build it from scratch. Most everything was there in the library ecosystem. For compilers, that's less relevant because compilers don't really have dependencies, but having a nice parser generator for me is good, and Rust has one. It's called Lollipop, and it works. And a parser generator that works is better than one that's like super advanced, but you can't configure it.
I guess like I mean, it is supposed to be for your own like unique language after all, so it's good if it's like flexible. But it's interesting what you said there about like Rust being good for prototyping, because I've seen there was this very good, like very thorough post from someone from the game dev community who was like, I don't know, they were tired of Rust, and they've developed like 3 games in Rust, I think, and now they were like not very happy, and they said they were gonna like switch to doing Unity and .NET.
I think I read this. I think they were using Bevy. I think. That's
probably the one.
Well, one of the limitations was modding, which is reasonable. I don't know how you would mod a Rust game, to be honest. Or really, plugins for a Rust program seems like a not great user experience. But I think, for game development, it is probably reasonable to. Well, there's 2 kinds of people, right? There's the people who build the game engine. There's the people who build the game, and never shall the 2 meet. So if you're building a game, you're probably better off not building the engine, just using Unity or Godot or whatever is good now. Yeah, for that particular thing, I don't have really any experience with graphics or game development, so I can't really speak to this, but I think using a more mainstream choice is probably good. But for like backend web services, I think Rust is like a perfectly cromulent choice. You know, it's better than Go. It's the type system is sounder than TypeScript. The ecosystem is pretty good. The tooling is pretty good. I mean, the only thing that sucks is the build times.
Yeah. I've heard those are not great.
Yes. So I don't know where to attribute kind of the blame for that. I think part of it is just LLVM, but also part of it is kind of intrinsic to the way Rust's module system is designed.
Yeah, the compilation unit is the crate, right?
Yeah, exactly.
I mean, yeah, and they sort of have the same, like I do a lot of work in F#, and they kind of have the same problem there. It's like, the compilation unit is the project, which means that like, even if you touch tiny bit in a project that maybe other projects depend upon, it's like, have to throw everything away and like rebuild it.
It's horrible.
Yeah,
I think it's I would call it a design flaw, because the only thing that this enables is you can have circular dependencies within a crate, and I'm like, I don't want to have circular dependencies within a crate. It makes the design worse.
Yeah, it's kind of an anti-feature. Like when you think about it, like I'm not, F# doesn't support it, and I can't really say I've missed it ever actually.
I would call it an anti-feature, but the build times are really bad. That's one thing I was paying attention to when designing Austral was the modules have to be separate compilation units, at least conceptually. And see, it's such a it is hard to predict from the design of the language what the compiler's performance is going to be. Or like the asymptotic performance is going to be, because it's just so costly to build a compiler and to build that you really have to test it empirically to figure it out. But then building a compiler takes so long, and you can never know, is this the most optimal implementation of like this compiler. But I think as a general rule, doing everything with maximal separate compilation seems like a great idea. And then monomorphization, a lot of the compiler slowdown is blamed on monomorphization. And that, I mean, I just kind of don't see the alternative,
And sorry, just to clarify for listeners, this is when you take like a polymorphic thing, like a generic, and then, I mean, basically there are two ways of doing it, right? And one way is to sort of like do it the same way like, C++ templates work, which is every case where you use it, you sort of inline the polymorphic use and turn it into like a concrete type, right? And I guess this is how Rust does it.
Yeah, the alternative way to do it is that in languages where every value is boxed, like Java, you can just have a single, if a generic function can just correspond to like a single implementation, where the implementation just takes, because ultimately all the arguments are just pointer-sized arguments, and as long as it doesn't depend on anything particular about the type, like the size of it, which you may be able to recover at runtime. As long as the function doesn't use anything about the type, you can just turn it into a function that takes and returns pointers, and that's really good, because it produces a lot less code, and so the code fits in the iCache better. But in a language where types are unboxed, like semantically, like in Rust, I don't see how you do it other than monomorphization. You could have a bunch of like tricks to share implementations. Like if a generic function doesn't contain a call to size of transitively, it can probably be the implementation can be shared for all monomorphs for types of the same size. So any type of size, four integers can just use the same implementation because it doesn't depend on anything. Actually, probably the size of is like fine. Like there's like monomorph sharing techniques that you might be able to use, but other than that, you have to do it. I mean, I don't see the alternative.
Yeah. And I mean, first and foremost, I guess it would like violate the user's expectation of, because like Rust is supposed to be able to be used in cases where you have like very stringent memory requirements, for example, and like every bit of runtime type information that you add sort of piles on, and like if you're targeting like desktop or a phone or something, a few bytes of memory here and there, I mean, it doesn't matter. But if you're programming for like a microcontroller, like you have to be mindful of that stuff. So then you're left with monomorphization, I guess.
This is something where it's hard for me to qualitatively judge because you broadly speaking have two approaches, right? Like you can monomorphize, and that's like locally faster but generates more code bloat, and you can do like dynamic dispatch, which requires more memory and it's like locally slower, but it generates less code. And there may be circumstances where monomorphization generates so much code that everything is constantly getting kicked out of the instruction cache, so it's actually slower. And where dynamic dispatch, because it generates so little code, it may be locally slower, but because of branch prediction and because there's less code, everything fits in the I cache and it's actually faster. And like the function that determines which of monomorphization or dynamic dispatch is faster, it just depends on such a complex conjunction of circumstances that it's hard for me to judge where, in what circumstances is one better than the other.
Yeah,
but
CPUs are so complex nowadays. It's like it's not like the olden days where you could sort of draw it out on graph paper, like this is all the stuff that's gonna fit in like the L1 cache or whatever. Like now it's just it's just branch prediction and wizardry and like lots of crazy stuff. But I was thinking about something you said there, like the thing with Rust again, like when for example, like when writing compilers, does the memory model of Rust get in the way? Because I'm thinking like when you run a compilation cycle, that's pretty much like a one-off thing, right? You start a program, it does its thing. So I imagine, and also like you have a bunch of like this kind of like tree data structures, etc. And I don't know, maybe it's just I'm not a good Rust programmer. I will freely admit that, but doesn't that get a bit harder with Rust?
Well, there's the argument that like for a compiler, like a language like OCaml, which is garbage collected and functional, is a better choice. I think one reason why Rust might be a poor choice for like a bootstrapping compiler is that there's always a temptation to do this like really high performance, like data oriented design with like structural arrays, and everything's like gorgeously high performance, but then everything's so optimized you can't really change anything after. But I think you can just, if you don't care about performance, which you don't have to for a bootstrapping compiler, for a prototype, you can't just write OCaml flavored Rust. You can't just like, when defining your abstract syntax tree data type, you can just make it a tree of pointers and just operate on it with recursive functions. So just make it like really very inefficient, but straightforward. You don't have to do like, data-oriented sea of nodes, whatever thing that's faster.
Like arena allocator is a term I've heard thrown
and
around
arenas
a bunch.
and like indices and everything's magical and cache aware. You can just write some like really inefficient functional code that does what you mean and it's like efficiently testable. I think that's a reasonable approach. The memory model just gets in the way to the extent that you want it to, I suppose. In a compiler, you could just like allocate everything and not have any deallocations in a batch compiler. But I think the kind of linear type semantics, it often lets you write like better APIs than you otherwise would be able to. So that's still a valuable thing to have. And you do have the benefit that you do have this like really high performance ceiling with Rust. So if the compiler is unacceptably slow, then you have the option to like rewrite the internal representations to use more efficient representations, to turn the trees into an array of nodes with internal index pointers and that kind of thing. I think I don't think it gets in the way. I think it really is a matter of like the design. You can design the compiler such that the Rust ownership model isn't a huge burden.
Yeah. Okay, you just have to like resist the temptation to make it like ultra performant on the first go.
I think for a bootstrapping compiler, the goal is to be able to like change your ideas, and I think that's just intrinsically incompatible with performance optimization, because performance is about tying everything together, and change is about modularity.
Yeah, I guess that's a fair assessment. It's funny as well, like as far as I remember, the first versions of Rust before it became self-hosting were also written, like the compiler was also written in OCaml, I think.
Yeah, well, but there was no Rust to write it in.
Yeah, exactly.
Yeah, I mean, I think back in 2008, things were so much more primitive, like tooling-wise. Like, I remember, things like linters were a novelty, back in that time.
Yeah, 2008. That was like, and language server protocol wouldn't come for another, like, I don't know how many years.
6.
6, or was it in 2014 that they came out with like the...
Yeah, I think so. Well, I entered the industry like 2012, and back then what we were doing was like we were using Vagrant virtual machines. Docker, I think, existed, but it wasn't super popular. We were deploying with like Ansible and SSHing into servers, and it just seems so archaic back then.
Yeah. But yeah, I mean, those I still have like still remember. I have fond memories of Ansible. I thought that was like just the right level of abstraction for me personally.
I feel that there's something comfortable about it, even though in the end you do want something more like Nix.
Oh yeah. I mean, Nix to me it feels like I've never like I don't know. Maybe it's just like I'm a like generational Kubernetes hater or something. I just I don't know. It sort of like never really made sense to me. I mean I can see why Google uses it, but it feels like if I just have like a few physical machines or like a few VMs, like I can manage them by hand, and like when something goes wrong, which it always does, I can the machine is still there, I can access it, I can look at the logs, whereas like I don't know, it feels like Docker was always such a huge jump up on the abstraction ladder, where like when it works, it's great, it's perfect, like just ship as many containers as you want, wherever you want. But the moment something breaks, it's usually so hard to diagnose. It's like, can I look at some logs somewhere? It's like, no, that was on the container that was in the cluster before, but that's gone now. It's like, oh, okay.
Personally, I like the ephemerality.
Yeah.
When it comes to like infrastructure, just like Docker on ECS, brother, I don't want to SSH into a server ever again. Just ghostly, immaterial infrastructure that you wave your hand and it ceases to exist. It's delightful. And I never used Nix for like a professional kind of like project, but I used to use Nix OS as my daily driver, and it was simply delightful. Like being able to configure the entire system, top to bottom, with like a single file, and everything's just like rock solid, delightful.
Yeah. No, I've actually never used Nix, but I sort of like, I don't know, it's sort of, to me it feels like a much more sensible idea. Instead of like, it's like that old saying where like, any problem can be solved with another layer of indirection.
Yeah.
That feels like it's like the Docker philosophy in a nutshell. Like, just keep stacking VMs on top of each other until something works. Like,
yeah. Docker is just it is very stateful, and it's just absurd. The idea of like, oh, it's reproducible, and you do an apt-get update within the Docker file, and it's like, well, this makes no sense. You just have to like, it's kind of it is a compromise. It is a reasonable compromise solution, but you just have to solve the problem at a slightly more fundamental level. And I think Nix kind of does that. And it's uncomfortable and hard to learn.
Yeah.
But maybe somebody will do it better.
Yeah, I don't know. Like, feels. I don't know. How do you know? Are you familiar with Unison, for example?
Yeah, a little bit.
Yeah, I mean, to me, that feels like a better step. Like, I mean, because basically, like the elevator pitch for Unison is like, basically you don't have code as files anymore. Like the code lives in a database, and when you want to change something, just push changes to the database. I mean, to me that has always felt like, or the issue I have with all this like Kubernetes etc. is that they feel like they sit on like an uncomfortable middle ground between something that's completely abstracted, like where infrastructure is abstracted away, and where it's like very concrete, because it's not completely gone. It's more like, I mean, the whole stack of operating system, runtime, virtual machine, etc. It's all there, and like at those are still like fallible components. So they're not really gone. They're more like, swept under the rug, kind of. Whereas in like Unison or for that matter like Cloudflare functions and stuff like that feels like more true to the vision of cloud, basically. Like,
I just don't know how much it's my only thing with Unison is that it's changing a lot of things at the same time. It's like like version control and text editors and programming languages and like package management, it all has to like change at once. And
I don't know exactly what, like, the if you sort of like trace back the lineage of Unison, like what was the first spark, but like the I think if you're really serious about like getting rid of infrastructure, etc., and like just abstracting away that is not everything but like business logic, I think that's sort of where you end up, because like, files and things like that, I mean, it's you sort of get this problem of multiple sources of truth. So I don't know. I'm gonna try to dig deeper into Unison in another podcast episode. 'Cause it's a very, very fascinating piece of technology. But to circle back a bit on like the whole Rust versus OCaml thing. So you're saying that like it's perfectly possible to prototype things fast in Rust, and you get a very nice developer experience as well. And I guess the drawback is that like the compiler, which I understand is quite fast in OCaml, can be a bit like slower in Rust. Is that like?
Yeah. You often have to in Rust. You often have to like split your project into crates just to make it a bit faster, and it's a very effortful process, especially if you're starting from a big monocrate project and splitting it. So when I start a project that I imagine is going to be on the order of like around maybe less than 10,000 lines of code or five-figure lines of code, I usually start with like a multiple crates thing and try to keep the crates very small and keep the crate graph very parallel. And it's debatable how much faster that makes things. Because it's so effortful, you can't really measure the before and after effectively. But you can at least get to a point where like a local change doesn't involve rebuilding the entire thing. And so it feels a bit more agile, especially like the LSP feels a bit more agile when you're doing a multi-crate project.
And how just to give an idea of like how long it takes, if let's say you have this 10,000 lines or so Rust project in a single crate, like how long approximately are we talking here in like build times?
That's hard to say. I think on my computer, the thing I do always is like cargo check, just the type checking step. And in a single crate project, that will take kind of like just for 10,000 lines, it will be just slow enough that it kind of takes me out of flow, like a second or two. Whereas in a multi-crate project, it just might be faster, and like 0.3 seconds. And analogously, with the LSP in a monocrate project, everything just feels like it lags a bit more. Whereas in a multi-crate project, it's just it feels more responsive. The actual build, not type checking, but proper build times, that's hard to measure because I really only mostly do that on CI, and CI, the conditions are always changing. It's hard to know what the cause of a slowdown is, but the cargo build dash release for 50,000 lines of code in like a GitHub Actions runner. Actually, most of the time is spent on the dependencies, so it's actually hard to know how much time is. But it's just incredibly fucking slow. If you're using Rust professionally, you just have to pay up for like the 4, 6, or 8 core GitHub Actions runners and just let them take care of that. Because it's just unpleasantly slow otherwise.
But and I understand what you're saying. Like building is it's a kind of different beast, and I mean there are a bunch of optimization flags you can play with, and probably then you start getting into the territory where like a lot of the slowdown is coming from like LLVM and not Rust itself.
And the linker and all that stuff. I'm not a big configuring things guy, so if I hear, you have to put this flag in your cargo.toml to make it fast, I'm like, no. It should either be the default or just fix it. I don't want to put flags in anything.
Everything should work. You should get like the most reasonable thing. Should be the default.
I don't want to be the flag tuning guy.
Mm. Like pulling a lot of like, I want the big O here, or like O1 is the no. Yeah, but that's interesting. I thought it would be much worse actually. Like, but a couple of seconds on a reasonably fast machine.
Well, for type checking, yes. I mean, I'm just very sensitive to anything that just kind of like takes me out of flow and is annoying, because it's kind of like the death by 1,000 cuts. You experience that it's a little slowdown, but you multiply that by like running cargo check 10,000 times, and it just becomes extremely annoying.
Yeah, I guess testing is a bit tricky as well.
Yes. That's another aspect of Rust, which is that because of the ownership model, it's much harder. You can separate interfaces from implementation to do like mocking, but it's very verbose, and it just requires writing a lot of like trait code, and I haven't quite found like a good way to do it that's like comfortable, because there's a whole debate to be had here. People will argue endlessly about like, is mocking good, or like what does mocking even mean? But like the point is, I want to be able to test like a workflow without testing transitively the side effects. I want to be able to test a workflow without actually spinning up a database. And for that, you need some way to separate the interface from the implementation. And in Rust, that's just a lot more complicated than in a language like TypeScript, where you can just pass like a closure or like an interface type, and it's all very easy.
Yeah, that's interesting. Like so like this classical thing of like, just have a dependency injection, etc. That doesn't work as well.
Well, this may be a skill issue on my part, but I think it's a problem, and I have not. Yeah. I have yet to figure out like what's the way to do it in a way that's like conceptually reasonable, but also not very onerous to write. Because if I have to write 5 times more code to make something testable, well, you start to get lost in like what is the actual code. You start to get lost in all the machinery of testing.
Yeah. One thing that I forgot to ask actually before was, you mentioned a bunch of times that like compiler, it's a pretty big project, and I definitely see that like it's like there are good reasons for it to be complex. But where would you say like most of the complexity comes from? Because if you look at the basic, if you read a blog post on like, I don't know, basic type checking, for example, you're like, look at this elegant Hindley-Milner implementation. It's just 150 lines of code. And look at this parser. It's only like 100 lines of code. And of course, I realized that those are toy examples, but something I'm curious about is like, in Austral or in Pro compilers in particular, like where do you notice like the most or the biggest differences between like these toy examples and a real world production thing? Where does the complexity come from?
I think, well, when I look at the Austral code, the biggest kind of like region of code is the type checker. Which is weird, because you feel like type checking is in a way so brain dead. Most of the time it's like, you have a function, so you have the list of the types of the parameters, and then the list of the types of the arguments, and they have to have the same length and they have to match. But then there's all these subtleties.
How hard could it be?
Yes, how hard could it be? It's just you check that the things are the same, and then it's like, well, actually, not all functions are functions. Some of them are functions and some of them are like type class methods. So you have to do the type class resolution. And, functions can be generic. So you're not just checking that the arguments, in a language like C, in a 0th order language like C, you are just checking the arguments against the parameters, because the types, there's no generic types and there's no subtyping. So an int is an int and that's it. But in a language with genetics, you have to like, you don't compare types for equality. It's more like you match a type parameter against a type argument, and you get a list of bindings of parameters to values. So the return type of a function is not just the return type. It says in the function declaration, it's the result of like doing that matching on the parameters and argument lists, and taking the resulting mapping of parameters to types, and then applying that mapping to the declared return type of the function, and that gives you the concrete return type of that function application. And then there's all, and that's for a language like Austral that doesn't have type inference, where type information only flows like upwards, and it's already like so complicated. And in a language that has all these like complex features like type classes and polymorphism, and you also have type inference, well, that's very tough. It's, you just end up writing a lot of code. I remember just finding this with writing the Austral compiler. It was type checking for most things was very simple. It was comparing the arguments to the parameters basically. But then the type checking for functions, it just kept going like deeper and deeper. It's like, well, first you have to discriminate, what kind of function this is, and then if this is a type class, well, you have to do the type class resolution. And if this is a generic type class, well, actually you have to take special care, because first you have to like check the parameters for first you have to type check the method call, but then you have to use those parameters to derive like the particular type class instance that you're working with. And it's just you're 10 layers deep into this, and then you have to call out to like the instance resolution algorithm, which itself is very complicated. And this is partly why debugging a compiler is so hard, because all the interesting stuff happens 50 layers deep in this context, this very rich context that you just cannot reconstruct in a unit test, because you cannot write a test case that has like the code and the state of the environment that you want. It's just, you will be writing so much test code, you would never be done. And another
extremely
thing,
brittle test code as well.
Yeah, exactly. Like you can't change the internals at all without changing all the tests. And outside of type checking, there's also like the environment, or the symbol table, depending on like how you call that. Surprisingly, there's very little literature on this aspect of compilers, like how declarations are parsed, stored, and then retrieved. It's actually a hard problem, and I never really seen anyone address this, because in all the toy examples, it's just like a hash table. It's just worthless. And in all the production compilers, they have some sui generis thing. And in the Austral compiler, I try to be principled about it, but it's just this very huge ad hoc database. And just the process of getting the declarations, it's kind of like everyone knows about type checking. Like that's a standard part of the vocabulary. But I don't know if there's a name. I think Ada calls this elaboration. I don't know if there's a name for the process of getting the top level declarations checked for correctness and slotted into the environment. That doesn't seem to have a name, even though every compiler does this.
Yeah, that's interesting actually. But I agree. Like it feels like most of the literature, it just says like, oh, this goes in the environment. And then it's okay, well, what is this environment exactly?
I think compiler textbooks are worthless. I don't know. They all spend, like the Dragon book is horrible. It's all 600 pages on parsing and like 45 pages on type checking, and then 300 pages on instruction selection and the backend. And it's like, okay, how about wait a minute? This is okay. Writing a parser, that's one thing. Writing a backend, well, you should do that once. That's LLVM or whatever alternative to LLVM you're building, because LLVM is very big nowadays. What about the middle is where all the magic happens? The compiler front end, from parsing to elaboration to type checking, to all the semantic analysis things you have to do. Before anything, like before you even get to the point where you're even thinking about execution or emitting any code, there's so much work you have to do to validate that the code is correct, especially in modern languages that have more advanced features. And there's just very little literature on doing this in practice. There's toy examples, and there's like papers about you have your turnstile notation, and then but how to build like a production quality compiler for a real practical programming language. That's not something there's a lot of literature about.
No, but so if someone would want to start to, or let's say someone wanted to write their own like production grade compiler, or get into like programming language theory and design, like what would be a good learning path you think? Do you have anything you could recommend?
Right. I took a very strange path to this, so it's I hesitate to give advice. I think the first programming languages book I read is not any of the standard textbooks that everyone recommends. It's not data structure. It's not like Introduction to Algorithms or the Dragon book or any of that stuff. It was actually this very obscure game development book called Game Scripting Mastery by one Alex Baranese. Okay. It's an old, very obscure book. But it's very practical. So like for a teenager who doesn't know natural deduction, it was actually a very good way to get started, because it was very practical minded, and it goes through building an interpreter, building a parser, building, I think, a simple compiler. It's very hands-on. Not sure if I would recommend it today, but that's just factually how I got started with this. And I wrote a blog post. Yeah.
Have you read the Crafting Interpreters book by?
I think I read some chapters of it on the website, but I haven't read the whole thing.
Yeah.
But I thought it was what I have read. It looks good.
Yeah, I've started, like, I haven't finished it. I started working through it. I know I'm a bad. I also have a very strange methodology of like learning. I sort of get bored easily, have very poor study discipline, etc., etc. So I don't know. I'm not an exemplar either, but I think that's it is a really it seems like a really good book. The problem with that was that I was more interested in type checking, and you're not building a type checker in that language. So, but sorry, you go ahead. You were had a blog post.
I wrote a blog post about the design of the Austral compiler, but it may be too high level to be useful. And also, a number of the design decisions are very kind of functional programming and OCaml specific. And so that may be a limited utility, and it's also just not concrete enough necessarily to be useful. And then there's a tool I've been meaning to learn for a while that's called PLT Redex, and it's like a Racket sublanguage for specifying the semantics of programming languages.
Okay.
It's kind of like writing the turnstile notation from PLT papers, but in like an executable, checkable format, which is something I've always wanted. Like if I'm writing a bunch of like LaTeX code, well, that's worthless, because how can I know that I made a mistake?
Yeah,
it's like writing code on paper. It's absurd. I want some kind of some kind of integrity checking to make sure that, you know, that these things at least make syntactic sense. So that's something I've been meaning to look into. And then being able to read the type theory notation is good. I think the standard textbook here is called Types on Programming Languages. I think if you read the first 5 chapters of it, you have maybe actually 3. Okay, 3 to 5. Then you have like kind of like the conceptual toolkit to understand those papers. The rest of the textbook is kind of like case studies of like, here's how different language features are formalized in this notation.
So like, you know, it describes like, okay, how would you, I don't know, implement like methods?
Yeah, like subtyping, that kind of thing. It's worth like skimming. But then, yeah, the basic things like how do you define syntax and how do you write semantics in like natural deduction syntax, and it's worth reading a bit about logic to be able to understand, because a lot of the type theory stuff is just kind of implicitly built on mathematical logic. So having some foundation in logic is useful to be able to read like the natural deduction and understand what it means. But then every PLT paper really has its own notation.
Yeah, I've noticed that as well, like, you know, slight variations.
Yeah, they all use like turnstile notation, and they use roughly same syntax for defining the BNF kind of like syntax, but they usually invent some kind of shorthand for like language specific constructs, and so you have to read very carefully the prose to figure out what they're doing with the turnstiles. And then each paper is kind of like its own case study. Something I've been meaning to do for a while is a blog post that teaches people how to read this PLT notation. And I think the way to approach it is to take a couple like random programming language theory papers and just essentially write an annotated version of those papers, which is like, okay,
that would be really nice.
Yeah, just walking the reader through it and explaining, well, this inference rule means this, and this particular notation that they're using means this. I think that's like a good practical way to learn.
Yeah, that would be awesome actually, to have someone like, you know, walk through like concrete and specific examples. Also, quite recently, like Alexis King made a great post on like I think it was on the Lang Dev Stack Exchange, where she made like a really good intro to the Gentsen like turnstile notation.
Yeah.
So I think if you just want to like I don't know, a crash course in that, I think that's a good place to start, and I'll make sure to link to it in the show notes. Yeah,
I also think it's worth studying a little bit of mathematical logic beforehand, because I mean there's a good textbook, there's a good like lightweight intro to logic textbook called like For All X Calgary. That's the version I read. There's like the city names. It's kind of like a series of books where people keep making variations or naming them after the city they live. It's very weird, but anyways, it's like an easy introduction to logic, because when you have a little bit of like logic and a little bit of like knowledge of like the natural deduction notation, it actually becomes, the programming language stuff becomes kind of empty. Like I learned mathematical logic first, and then when I read the first few chapters of the Types on Programming Languages textbook, it's like, well, this is just set theory and like natural deduction, right? It's kind of empty. And okay, this is like, there's a couple little domain specific things, but otherwise, it's just like proof theory, mathematical logic, and term rewriting. And it's like, I already kind of know this. And then the difficulty is really just that each paper is using this sui generis like dialect of the notation, where they're just inventing their own stuff, and it becomes a bit more social than technical. You know, you have to like figure out the local dialect.
Yeah. Like I remember I read some paper about like bi-directional typing. I think it was like, you know, all of a sudden they have this like, you know, arrows pointing up and down. Like, you know, okay, what's going on here?
God. Yeah.
But yeah, like you said, yeah, you have to sort of pay attention. At least they're usually pretty good at like explaining what the new symbols mean. But like you said, like they might not be formally like well defined. I guess we're sort of at the point that like temporal logic pre TLA plus basically, like and that PLT regex thing kind of sounds interesting in that regard, because like you said, it's when you don't have any way to like execute the thing, it's very easy to accidentally or by omission, like, you know, introduce inconsistencies, etc.
Yeah. Well, even not even executing, just even basic things like checking the syntactic correctness of the rules is kind of missing. And then the problem with doing it all on paper is then the proofs, for example, the proof that the type checking algorithm terminates, or the proof that the proof that the type checking is sound, those also have to be on paper. And I'm like, well, it's 2025, you know, there should be a formal language where we can express these things and also express the proofs, and the proofs should be checked by a computer. And I guess, I guess I had to learn Lean, maybe. I don't know.
Lean seems big right now. Lean seems super hot.
Lean is pretty hot, but it's kind of ironic, you know. It's like the computer science people, shouldn't they have solved this? Like, they're doing literature. They're doing literature to describe programming languages. That's kind of seems contradictory. Like, shouldn't there be a formal language where we can do this more rigorously?
Maybe they just think it's nice to take a break from the computer.
Yeah, that's true. I mean, you can write the natural deduction stuff by hand. I guess that's very wholesome.
Yeah, it goes very well, like, you know, with the graph paper. It's like, you know, graph paper and a ruler, like, you know, so you can write all those long horizontal lines. But basically, you're saying that in 2025 we should be able to do better with the, like, you know, the notation than just like, you know, oh, trust me, bro, it's solid.
Yeah, like I would be able to. I mean, I guess the ideal thing would be, you can describe the BNF grammar, and you can describe the inference rules for the type, whatever, and you can, from that you can extract a parser, a compiler, and a proof, if any, that the type checking is sound, and that it terminates.
Yeah, that would be
sound, set difference, recursion, which is of course unsound. But it would be nice to have these things be a bit more automated. But it's one of those things where, because the problem with trying to design a meta-formalism for programming languages is, well, that's probably just a Turing-complete programming language, because there's so many features that a programming language can have, that you probably just end up getting something that's completely intractable if you want to represent everything. Remains
to be seen, I guess. But yes, I think we are running a bit. We're running out of podcast time. But again, thank you so much, Fernando, for agreeing to come on the podcast at this early hour in Australia.
Thank you for inviting me. It's my privilege.
Yeah. And Where can people find you if they want to? And before we quit, or before we hang up, I just have to say, like, I really enjoy your blog. It's very nice. I don't understand how you have time to write such well-written articles while doing a bunch of other things as well. But
well, I'm currently unemployed, so that helps.
I guess that helps. But you have a good track record as well. It's
yeah. Thank you. Well, where can people find me? The blog is at borretti.me. That's BORRETTI.me, and I'm also on Twitter at Zetalairae. That's Zetalalyrae, like the star.
Yeah, we'll put the link in the show notes as well for the listeners.
Okay, thank you. This was really good.
Yes, great conversation, and thanks again for getting up super early. It's your morning now, and it's my night, so I'm going to bed. But thanks again. I'll see you later, Fernando.
Thank you. Take care.